Session 3.4 Polynomial Functions, Graph, Applications, and Models. This is the summary for the transformation rules for functions. If you have the f of x, when you add a constant on it, then you're gonna shift this graph upward, okay, upward d units. When you subtract a constant, you're gonna shift downward d units. When you have x plus c within the x here, you're gonna shift horizontal, shift c unit to the left. And that one, x minus c, that will be shift c unit to the right. And that one, negative of f of x, that will be refraction over x-axis. If the negative is inside here, so f of negative x, then there'll be refraction over y-axis. Okay, you're gonna be looking the y-axis and then there'll be refraction. A times f of x, we worked on this guy already. Remember, we're working on y equal to x squared. When we have, for example, y equal to 2x squared, 2 is strictly greater than 1, then the parabola gonna be close to the y-axis. If your a is between 0 and 1, that will be a wide, like this one. Okay? The b here, talking about like the horizontal compressions. When b is greater than 1, for example, f of 2x, okay, then you're gonna have horizontal compressions. So the graph is gonna be a little bit closer also. Polynomial functions of the form f of x equal to x to the power of n and n greater than equal to 1 are called power functions. So you could see on the left hand side, this is all n equal to even. Okay, y equal to x squared, this is gonna be the parabola, just like the U shape. If we increase the n, if n has a higher power and an even higher power, then you're gonna see the graph is gonna be more to stick with the x-axis here. Okay, a little bit larger like that way. And on your right hand side, this is talking about when n is equal to odd number. You're gonna be looks like this. When you increase the degree, you could see the n to the power of 5th is much more close to x-axis, just like the idea with the x to the power of 4th. Graph f of x equal to x squared plus 1. Determine the largest open interval of the domain for which each function is increasing or decreasing. So we could look at f of x equal to x squared. It can be looks like the blue one, like this. Right? When we want to add 1 here, so adding like d unit, that means we're gonna shift this graph upward 1 unit. Okay, it's supposed to be, the turning point here is supposed to be 0. But then since we add 1, so we're gonna shift all the graph 1 unit upward. Okay, which part is gonna be increasing? Basically, for the odd function here, the whole graph is also increasing. So we could say the domain will be increasing from negative infinity to positive infinity. Okay, another one, x minus 2 to the power of 5th. And this is also the odd function, just like this guy, right? And the first example, we have the function x plus 1. That's why we shift upward 1 unit. But for the second example here, this is within the f of x, x minus 2 to the power of 5th. So this one, we're gonna shift to the right 2 unit. Okay, 2 unit. It's supposed the turning point will be on 0. So gonna be turned to right 1, 2 here. And then same idea. The increasing function will be from negative infinity to positive infinity. Okay, this one, graph of f of x, negative 1/2, x plus 3 to the power of 4, okay? This is to the power of 4. That will be the even function. Looks like the U shape, okay? And then first, x plus 3, this is within the exponent. So we're gonna shift to the left 3 unit. And then we're gonna add the constant 5. So we're gonna shift upward 5 unit. And this one, since this is the negative, so that will be refraction on x-axis, means it's gonna be downward, going like this way. Okay, so going downward, shift to the left 3 unit, and then shift upward 5 unit. And then the A is gonna be 1/2, okay? 1/2 is in between 0 and 1, so the graph is gonna be wider, okay? Wider, close to the x-axis. Okay, shift to the left 3 unit, go up 5 unit. And then the graph is a little bit wider. Okay, think about it. What is the domain here? And then the domain for the function is increasing. So here, from negative infinity until here, this point, x equal to negative 3. Okay, at this point, that will be increasing. And then from negative 3 to positive infinity, that will be decreasing. And we use the brackets here. That means x can equal to 3. Okay, this is gonna be your maximum point. Okay, arc degree. Let's look at the polynomials. We always look at the higher degree for the polynomial. This one, we have a 2x cubed here. So you're gonna know the graph is gonna be look like that one. Okay, look like this. And then you could see after we factor out, we do have a factor x minus 1, x plus 2, and x plus 3. And these 3 points will be the 0. So x equal to 1, x equal to negative 2, and x equal to negative 3. Okay, we do have a 3 zeros here. Second one. This time, I do have a degree of 3 also. It's supposed to go on like this way, right? But we do have a negative. The leading coefficient is negative. So we're gonna reflect it by y-axis. So going another way around. And then after we factor out, we do have a 2 compressed zeros. We can't draw the compressed zero in here. So we only have a 1 0, x equal to 2. Last one, x to the power of 5th. So also, it should be going like this way, all right? And then after we factor out, we do have x equal to 1 and x equal to negative 2. You may ask like, hey, how do I know the graph is going to be going like that way? It would be going this up and then go down and then go up again. Yes, we don't really know, okay? We only can see like which one is going to be the zeros. And also, we know like the starting behavior and also the ending behavior. You could see when you have the leading coefficient, that's a positive. And with the odd degree, so it always like going increasing. Always starting like increasing. Increasing here, and this is gonna be odd degree, positive, increasing. When you have a negative leading coefficient, and with odd degree, you're gonna be going decreasing, okay? A polynomial function of even degree has a range of the form from negative infinity to k, or k to positive infinity for some real number k. Here are 2 typical graphs, even degree. So you know when you have an even degree, the graph is gonna be decreasing and then increasing. Okay, it's just like the U shape. After we factor out the even degree, we could see for this example, we have 1, 2, 3, 4. We do have a 4 zeros. Right? X equal to 1, x equal to negative 1, x equal to 2, and x equal to negative 2. We know the starting and the ending behavior. Okay, it's going to be decreasing and increasing. But when we have a negative leading coefficient with the even degree, then the graph is going to be going downward. Okay, and then for this example, we do have 1, 2, 3, 3 zeros. X equal to negative 2, x equal to negative 1, and x equal to 1. The behavior of a graph at a zero depends on the multiplicity of the zero as determined by the exponent on the corresponding factor. So the behavior of the graph, you're going to look at the factor. Like this example, we could see x plus 2 is a factor of multiplicity 1. It means we only have a first power here. This is 1, x plus 2 to the power of 1. Then the graph is going to be causing at the x-axis at -2 and 0. Okay, the graph is going to be going strictly up or strictly down. Okay, because x plus 2 is the factor of multiplicity of 1 here. Okay, you could check that here. Like this one, x minus 1 to the power of 1, x plus 1 to the power of 1. All of them, they do have the power of 1 here. So that's why the curve is going to be cutting on x-axis, strictly. Okay, so this is the first one. Second one, when x plus 1 is a factor of multiplicity of 2, that means when you look at the factor, we have a x plus 1 square. Okay, square. This means that it touched the x-axis, then turns and change behavior from decreasing to increasing. So when you have the square, it's gonna be just like the parabola. It's just like the U here. Okay, decreasing and then turning and then go back to increasing. Okay, this is the factor when you have a multiplicity of 2. Okay, the graph is always looks like either upward or downward and passing through at that point. Okay, another one. When you have a x minus 1 is a factor of multiplicity of 3, just like this guy, x minus 1 to the power of 3 here. This causes a change in concativity, just like here, just like when you guys sketch the graph with y equal to x to the power of 3. Okay? That is, look at the factor with the multiplicity of 3 here. Turning points and end behavior. The graph exhibiting functions of odd degree and even degree, so that polynomial functions often have turning points, where the function changes from increasing to decreasing or from decreasing to increasing. So turning points, a polynomial function of degree n has at most n minus 1 turning points. For example, if I have a degree of 4, then at most I only have 3 turning points at most, with at least 1 turning point between each pair of successive zeros. And the end behavior, we always look at the greatest degree. Okay, the ending behaviors, it depends on your greatest degree here. End behavior, for example, I have this polynomial. We only look at the highest degree. So I'm gonna look at the 2x to the power of 3. This is the same end behavior of these functions. It rises to the right and then falls to the left. End behavior. So for this example, first we're gonna look at it. This is an odd function, so we're gonna know it's gonna be looked at it this way, right? But then we have a positive coefficient, that's a 2. So we know that it's gonna be rise to the right and then falls to the left here. After we factor out, we do have a 3 factor, and all of them will be has the multiplicity of 1. So you're gonna see the graph is gonna be passed through at that point only. And this one, we do have a negative, so it's gonna be reflected by y-axis. And this time, we will have a rise to the left and falls to the right. Okay, so keep in mind that when you have a greater than 0, and n is odd number, you will have the graph looks like that one. Okay, you still see the dot 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 here. That means you're gonna figure out what is the zeros. But when your a is strictly less than 0, that's a negative, and n is odd number, then we're gonna rise to the left and falls to the right. When a greater than 0, okay, and n is an even number, for example, y equal to x squared, okay, you're gonna know that will be the U shape going upward. But when a is strictly less than 0 with the n even degree, so it's gonna be going downward. Okay, based on the discussion of n behavior, match each function with its graph. Okay, try multiple choice. Which one is going to be your graph A? Which one is going to be your graph B? Okay, let's check the answer. So you're gonna see A and C, this one going downward, this one going upward. So I'm gonna know this polynomial that with the even degree. Okay, the highest degree will be even. So either f of x or gx for A and C here. And then this one is going downward. So the leading coefficient should be negative. So I know g of x, that will be belong A. And then f of x, that will be belong C here. Okay, and then these two, B and D, we should have the odd degree. Okay, that will be h of x and k of x. And since this is gonna be y to the right, false from the left, so that will be positive leading coefficient, which is gonna be h of x. And this one is gonna be y to the left and fall from the right. So that will be the k of x here. Okay, so you should get C, A, B, D. Okay, this one. Use the symbols for n behavior to describe the n behavior of the graph of each function. So try to just sketch it. How's gonna be looks like for this one. So you do have an even degree, so either going upward or downward, right? And the leading coefficient is a negative, so it's gonna be going downward. And then B, this is the odd degree, right? So it's gonna be either going like that way or going like that way. And the leading coefficient is a positive, so it's gonna be y to the right, 4 from the left. Okay, graphing a polynomial functions. We do have a function x here, be a polynomial function of degree n. To sketch its graph, follow this step. Step 1, find the real zeros of f. Okay, we could find out the possible rational zeros. Remember the factor of p and the factor of q. Write it down. And then we're going to try to plug in the possible zeros into the f of x using the symplectic division. Once we find out the zero, we could have the factor. Okay, factor out. And then we're gonna find out the x-intercept. So we're gonna put y equal to 0. Means after you factor out, you do have a linear factor, then you're gonna solve for your x. That will be your x-intercept. And then we're gonna find the y-intercept. We plug in x equal to 0 and figure out what is your a0. That will be your y-intercept. And then use n behavior, whether the graph corresponds or wiggles through the x-axis and the x-intercept, and select points as necessary to complete the graph. Okay, let's try to do this example together. So, write it down. What is your possible rational zeros? We're gonna look at the p, right? P will be the -6. And then the q will be 2. Okay, what is the combination of the possible rational zero? P over q. Okay, the 6, you could break it down to 1 plus 1 minus. So we have 1 times 6, 2 times 3. And this one, the 2, is only 1 times 2, right? Plus minus also. So the possible rational zeros, you get this. And then you're gonna try to pick in some easy number, like positive 1 or negative 1 or positive 2 or negative 2. Okay, you could plug it in, use your calculator to see if you got the zero. Or you can use the symplectic division. So let's try x equal to 2. Okay, x equal to 2. Use the symplectic division to see if you got 0 for the remainder. Okay, check your work. So x equal to 2, that will be the 0. So we do have a one factor, x minus 2. And then write down this quotient. That will be 2x squared plus 7x plus 3. Now, factor out the quadratic equation here. So you should get this. That will be your x-intercept, right? Remember how to find the x-intercept? You're gonna set f of x equal to 0. So x equal to 2, x equal to negative 1/2, and x equal to negative 3. Okay, step 2, find the y-intercept. You're gonna plug in x equal to 0. Okay, plug in x equal to 0, you're gonna get negative 6. So 0, negative 6, that will be your y-intercept. Okay, and then step 3, we're gonna look at the ending behavior. So look at the highest degree, that will be degree 3. This is an odd number. And then we do have the leading coefficient is a positive. So the graph is gonna be going like that way, right? Rise to the right and fall from the left. Okay, now look at the factor here. All the factor with the multiplicity of 1. Okay, so the graph is gonna be pass through negative 3 and then go up and then going down to negative 1/2 and then hitting the y-intercept negative 6 and then going up past through the 2. Okay, that's a y-intercept and all x-intercept here. And then ending behavior, rise to the right and fall from the left. Okay, this example. So I factor out the polynomial already. I just want you guys finding first the x-intercept. X-intercept, you're gonna set this guy equal to 0. So what did you find for the x? Okay, check your work. You should get x equal to negative 2 and x equal to 1. And then now, find the y-intercept. So you're gonna plug in x equal to 0. So f of 0, that will be equal to 8, right? So 0, 8, that will be the y-intercept. And then step 3, we're gonna think about what is your degree for this polynomial. We have an x squared and x squared. So when you add it up, that will be x to the power of 5th. And the leading coefficient will be positive 1. So you're gonna know the end behavior. It's gonna be rise to the right, fall from the left. Okay, and then we do have the factor x plus 2 to the power of 3. We do have a multiplicity of 3. So when you pass through the point x equal to negative 2, the graph is going to be going like that one. Okay, and then x equal to 1, we do have a multiplicity of 2. So when you pass through this point, x equal to 1, either upward like that way or downward like that way. Okay, try to put everything together. Okay, we have these 2 points. this is the multiplicity of 3. So it's going to be looks like that. That's kind of the turning point like this. And then we have the y-intercept. And you know x minus 1, we do have the multiplicity of 2. So it's going to be going upward. Okay, that's it.